If you've worked with virtual machines before, you've already thought about networks, IP addresses, ports, isolation. Docker handles all of these as well, but in its own way. Many containers need network access. They need to communicate internally with other containers and externally, outside the Docker host. We saw a simple example of this in the previous video, where we exposed port 80 to allow HTTP traffic into a web server container. Effectively, we allowed traffic from outside Docker to reach a container. This hints at something important. There is no inbound network access to containers by default. We have to configure it explicitly on a port-by-port basis. Outbound network access is a different story. We don't need to configure anything. If a container needs to reach the internet, perhaps to pull in some updates, it can do so by default. It will use the Docker host's IP address, so the traffic appears to come from the Docker server. Let's think about how IP addresses are assigned to containers. When a container starts, it is automatically given a private IP address, usually from the 172.17.00/16 range. These addresses are only accessible within the Docker host by default. If we want to, we can manually assign IPv4 or IPv6 addresses to containers. There are times this is useful, but in most cases, it's easier to let Docker handle IP addressing automatically. Internally, Docker has its own DNS server for container-to-container communication. As you know, when a container starts, it gets a name, either one we set manually or one that Docker assigns automatically. The internal DNS server tracks these name-to-IP mappings, allowing containers on the same network to reach each other by name. This is why we usually don't worry about manually assigning IPs. Containers just need to know each other's names in order to communicate with each other. Let's take a look at some of the network types available in Docker. The default type is called the bridge network. This is an isolated network. It lives within the Docker host. Multiple containers can connect to the same bridge network to communicate with each other. By default, there are no restrictions on communications between containers on the same bridge network. Even though the bridge network is isolated from the outside world, containers on the network can still make outbound connections to external resources. This might be for updates or something similar. Inbound connections are blocked by default. However, we can enable them on a port-by-port basis. You may recall from the previous video that we use the P parameter to expose port 80 when starting a container. This is exactly how we allow inbound HTTP traffic to the container. There is a default bridge network in Docker, but it is best practice to create your own. We can do this with the Docker network create command, followed by a friendly name for the network. To see a list of networks, use Docker network ls. You'll see a few created by default, as well as the one we just created. The driver column refers to the network type. Since we didn't specify one, Docker defaulted to bridge. To attach a container to this network, we started with the network parameter. The argument is simply the name of the network. If we omit this, the container joins the default bridge network instead. Now that the container is running, let's get some network information using the docker inspect command. This command returns a lot of information about the container. Look for the network settings section. This is where you'll find the network type, IP address, gateway, MAC address, DNS names, and more. Let's test that this network actually works. I'll start a BusyBox container in interactive mode and put it on the same network as the Ubuntu container. If you haven't come across BusyBox before, it is a lightweight Linux distribution packed with useful tools for testing and troubleshooting. From here, we'll run some simple ping tests. First, we'll ping by IP address, the one we got from the docker inspect command. Then we'll ping by container name. This confirms that DNS is working between the containers. The bridge network is good for isolation. It keeps containers separated from the outside world and from containers on other networks. Another network type that takes isolation to the extreme is the none network. When you attach a container to none, it has no network interfaces at all. It is completely cut off from all network communication. Why might we use this? Because not every container needs network access. We might have a container that simply runs a script to process some files on a volume. There is no reason to expose it to a network, and best practice says that we shouldn't. We can confirm it here. We're starting a container and issuing the IPADDR command to see some network information. As you can see, a container on the none network shows only a loopback interface. There are no other network interfaces present. It cannot reach anything, and nothing can reach it. A network type that goes in the complete other direction is the host network. When we use this type, the container shares the host's network stack completely. From an external perspective, the container and the Docker host appear to be the same device on the network. This is not a network type we would use very often. It does provide certain benefits, such as high performance because there's no NAT overhead, and it handles dynamic port ranges very well. However, it does not scale. If we start using a lot of containers on the host network, we are likely to run into overlapping ports and conflicts. For example, two containers cannot both listen on port 80 on the same host. So the host network has a time and place, but use it sparingly. One of the more advanced network types is the MACVLAN network. The purpose of this type is to place containers directly on the external network. From an external perspective, containers will appear to be regular devices on the network. Behind the scenes, Docker creates virtual network interfaces on the host to represent the containers. Each container gets a unique MAC address. This is a bit like having a virtual layer 2 switch inside the Docker host, connected to the external upstream switch. Containers also get unique IP addresses. However, these must be in the same subnet as the Docker host. There are some advantages and disadvantages to this network type. Containers are placed directly on the external network, so there is no port forwarding required. This can simplify firewall configuration, since each container can be referenced directly by its own IP. We also avoid port conflicts entirely, because each container has its own IP address, and therefore it has access to the full port range. We can even assign VLAN IDs, making it possible to configure trunking to an upstream switch. On the other hand, we may run into some problems. Like any layer 2 network, containers will see broadcasts, ARP requests, and layer 2 flooding. External switches may also cause problems. If port security is configured, a switch port may shut down when it sees multiple MAC addresses, which would break connectivity to the entire Docker server. The switch would need special configuration to support this. Also, some cloud providers do not support this network type at all. If you are running Docker in the cloud, MACVLAN may simply not work for you. And finally, containers on a MACVLAN network cannot natively communicate with the Docker host itself. This may not be an issue in your use case, but it is still worth knowing. I'll now show you how to create the MACVLAN network. Please keep in mind that this is not supported on Docker Desktop, so I'll be doing this in Docker Server. The first step is to find the name of the network card on the Docker host. We'll be needing this in the next step. Next, we create the network with the docker network create command. This time, we need the D parameter to set the network driver. In this case, MACVLAN. We also set the subnet and default gateway. The gateway here is a real router on the external network. The O parameter sets additional options. Here we pass the parent argument, which refers to the network interface on the host. That is why we needed to get the interface name in the previous step. And finally, we give the network a name as usual. The third step is to start a container and attach it to this network. As with other network types, we use the network parameter with the network name. This is also a case where we want to manually assign an IP address. It just needs to be something available on the external network. So I've made this a detached container so it runs in the background. If I open a command prompt on another device, not the Docker host, we can see that ping works without any issues. The last network type we want to look at is called IPVLAN. This is similar to MACVLAN in some ways, but it's greatly enhanced. The goal is still to make containers accessible on the external network, but with a slightly different approach. The biggest difference is that containers no longer have a unique MAC address. Instead, they share the host's MAC. This works around several of the problems we saw with MACVLAN. And as an extra bonus, IPVLAN can be deployed in either Layer 2 mode or Layer 3 mode. Layer 2 mode is the simpler of these two options. Just as with MACVLAN, containers get an IP address on the external network. It still must be in the same subnet as the parent interface. The key improvement is that it shares the host's MAC address. This means only one MAC is ever seen on the upstream switch port, so port security is no longer an issue. Layer 3 mode is a fully routed solution. There is a routed network behind the host's network card, and it behaves like a virtual Layer 3 router inside Docker itself. Containers get unique IP addresses, but in a different subnet to the Docker host. An important thing to remember is this. This requires external network configuration. You would need to add a route on your external gateway to point traffic for this container subnet toward the Docker host. So let's create a Layer 2 IPVLAN network now. Be aware that this is not supported on Docker Desktop, so I'm doing this in Docker Server. As usual, we start with Docker Network Create. The D parameter sets the network driver to IPVLAN. We set the subnet and the default gateway. Note that the gateway is the real gateway on the external network. The first option parameter sets the mode to L2, meaning Layer 2. The second option identifies the parent network interface, the one on the Docker host that connects to the external network. And finally, we give the network a friendly name. We would start a container on this network exactly as normal, using the network parameter. Let's take a look at how to deploy a Layer 3 network now. It's not very different from the one we just saw. But before I do this, I will need to remove the Layer 2 network I just created. This is because I can't have two IPVLAN networks using the same parent interface. We still use the IPVLAN network driver. We set a subnet, which is different this time to the host's subnet, but we do not include a gateway. That's because in Layer 3 mode, the Docker host itself acts as a default gateway for containers. The two option parameters set the mode to Layer 3 and identify the parent network interface. So that's all there is to the network configuration. A container is started as normal using the network parameter and will be given an IP in this subnet. Just remember to add that static route to your external gateway. So you've now got the basics of Docker networking under your belt. In the next video, we're going to be looking at customizing our own Docker images. And if you want this in full depth, hands-on labs, real-world examples, and complete coverage of everything we have touched on here,